Welcome to section 2.6 Matrices. We are using the text Discrete Mathematics and Its Applications by Kenneth H. Rosen, 7th edition. Thank you, and this is Dr. Gilbert, Eyabi. Lesson objectives. Today we would look at the definition of a matrix, matrix arithmetic, transposes and powers of arithmetic, and the 0-1 matrices. So let's start off with matrices. Matrices are useful discrete structures that can be used in many ways. For example, to describe certain types of functions known as linear transformations, and for those who are interested in graph theory, to express vertices of graphs that are connected by edges. And we will see that some more in chapter 10. In later chapters, we would see matrices used to build models of transportation systems, communication networks. Algorithms based on matrix models will be presented in later chapters. So in this section, we would cover the aspect of matrix arithmetic that will be needed later. For example, we would look at what it means for two matrices to be equal, adding two matrices, scalar multiplication of a matrix, and multiplication of a matrix, and then, of course, the 0-1 matrices. Definition. A matrix is a rectangular array of numbers. It has rows and columns. If we say a matrix is an m by n matrix, it means that it has m rows and n columns. So right here, this matrix has 1, 2, 3 rows and has 1, 2 columns. So it's a 3 by 2 matrix. Two matrices are equal if and only if, number one, they have the same number of rows, the same number of columns, and corresponding entries are equal. So they have the same dimension. Okay, so if we say a 3 by 2 matrix, it means the matrix has dimension 3 by 2. Notation. An m by n matrix is represented in this matrix form where A11, A12, A1n is such that the element A12 is the element that sits in the first row and second column. So this element right here will be the element that sits in the second row and second column. That is why it is A22. AMN is the element that sits in the mth row and nth column. So that is AMN. But we would not use this notation often, especially when it comes to proofs. We would use the notation Aij, and if there is no conflict of notation or there is no problem with the dimension of A, we would just say let A be the matrix Aij. If we're dealing with several matrices with different dimensions, then we can say let A equals Aij, and right here on the right we put M by N or P by Q or R by S to inform you on what the dimension of A would be. So we would simply say let A equals Aij denote the matrix where the element Aij is the element in the ith row and jth column. That is the element Aij, and that is enough to determine the entire matrix A. Let's look at a couple of arithmetic operations with matrices. Let's start off with addition. Let A be the matrix Aij. I'll prefer to use this right here. Let A be the matrix Aij, m by n. That means A is an m by n matrix. The elements in A are of the form Aij. Let B be the matrix Bij. The dimension is P by Q. Then A plus B addition is feasible if and only if M equals P and N equals Q. In other words, the addition of two matrices is feasible if and only if both matrices are of the same dimensions. And if that is the case, then A plus B, which is Aij plus Bij, simply equals the matrix Aij plus Bij. So I add corresponding terms. Example, that's the 3 by 3 matrix. That's the 3 by 3 matrix. So, addition is feasible. If I add these two, what do I get? I do 1 plus 3, that's a 4. I do 0 plus 4, that's a 4. I do -1 plus -1, which is -2, and so on and so forth. And the third thing, which we already mentioned before, but I would like to put it here again, the matrix A is said to be equal to the matrix B if and only if, number one, they are of the same dimension, and number two, Aij equals Bij for every Ij. Corresponding entries are the same. Okay, so these are some top 3 things we need to know as far as matrices are concerned. Now, let's talk about matrix multiplication. Before I get into matrix multiplication, I'll touch scalar multiplication first. So, scalar multiplication. Let alpha be a scalar, that means alpha is a real number, and let A be the matrix Aij. Then the scalar multiple of A, alpha A, is alpha times the matrix Aij, and that is simply the matrix alpha Aij, i.e., I multiply every entry of the matrix A by alpha, and that's all. Okay, so that is how we deal with scalar multiplication. Now, regular matrix multiplication. Let A be the matrix with dimension m by k, and let B be the matrix with dimension k by n. We can discuss the product A times B. Now, observe that A times B is feasible if and only if the number of columns of A equals the number of rows of B. So K must be equal to K, and the result is going to be an M by N. So when you put A and B together, you have to make sure that your number of columns here is the same as your number of rows. And secondly, when you're done, your answer, the result, is going to be M by N. Okay, so here's how it works. I'm going to use this example. Can we find the product of A and B? Is it even feasible? Can this multiplication work? So 1, 2, 3, 4, 1, 2, 3. So this is a 4 by 3. So A is a 4 by 3 matrix. And our matrix B, 1, 2, 3, 1, 2, is a 3 by 2. So 4 by 3, 3 by 2. You see, you have the 3 and the 3. So that tells you that multiplication is feasible, and our end result is going to be 4 by 2. Okay, so feasibility is given. Now, let's look at the multiplication itself. So how does the multiplication work? I take the first row, I multiply it by the first column. I put the answer in this first position. I take the first row, I multiply it by the second column. I put the answer in this position. I go to the next row. I take this row, multiply it by this column. I put the answer in this position. I take this row, multiply by this column. I put the answer in this position. I go to the next row. I take this row, I multiply it by this column. I put the answer in this position. I take this row, multiply by this column, put the answer in this position. Take this row, multiply by this column, put the answer in this position. And then lastly, I take this row and multiply by this column and put the answer in this position. So, multiplying this row and this column, how does that work? It's not like 4 times 5 or 3 times 2. How do I multiply a row by a column? Well, you'll learn some more about this in linear algebra. This row is actually a vector, and this other row is actually a vector, and we're looking at the dot product of 2 vectors using standard multiplication. Again, don't worry much about this. You'll learn it some more in linear algebra. But this is how we proceed. So this row times this column, it will be 1 times 2 plus 0 times 1 plus 4 times 3, and I put the answer right here. So for the first operation, is going to be 1 times 2 plus 0 times 1 plus 4 times 3, and that gives us 14, and it goes right there. And then I do the same thing for my first row and second column. it will be 1 times 4 plus 0 times 1 plus 4 times 0, and that gives you 4, and that goes right here. Okay, let's try this also, and then I'll leave the rest as simple exercises for serious students. So I do the second row and the first column, and that's going to go right here. So that will be 2 times 2, which is 4, plus 1 times 1, that is 5, plus 1 times 3, that is 8. And it goes right here. One more. Okay, let's figure out how we get this 9. Again, that will be second row and second column. So 2 times 4, that is 8, plus 1 times 1, that is 9, plus 1 times 0, that is still 9, and we have our 9. And I would leave the rest as simple exercises for serious students. The product of two matrices is undefined when the number of columns in the first matrix is not the same as the number of rows in the second matrix. So here's what we're talking about. We have our A, we have our B. This is an M by K matrix, and that is a K by N matrix, the K and the K. So multiplication is feasible. Again, I do my first row times the first column, and that goes right here. First row, second column, that goes right there. First row. So all the operations I do with the first row would go on the first row. You see that? All the operations I do with the second row will go on the second row. So this row 2 times the first column goes right here. Row 2 times the second column goes right there. Row 2 times the third column goes right there, and so on and so forth. Okay, all you have to do is practice a few problems and it will become second nature. It's beautiful. Commutativity. One of the things you learn from kindergarten is that A times B equals B times A. But what they did not tell you was that you were dealing with a set of real numbers, and so it was very okay to say 3 times 5 equals 5 times 3. But as you progress in your math journey, you come to realize that the set of real numbers is not the only set that we have around. There are all kinds of sets, including the set of matrices. And when we come to the set of matrices, commutativity does not hold. A times B does not always equal B times A. And a simple example is right here. A is the matrix 1, 1, 2, 1, and B is the matrix 2, 1, 1, 1. That's a 2 by 2, that's a 2 by 2, so multiplication is feasible. A times B would be 1 times 2, which is 2, plus 1 times 1, which is 3, right there. Unfortunately, I think the textbook made an error, so don't be mad at them. It's possible. And let's continue with the first row. So the first row and the second column, that will be 1 times 1 is 1, plus 1 times 1, that's 2. And then we move over. I want to do this again and again just so that it sticks and you don't have any problem with matrix multiplication. So let's go ahead with row 2 and column 1. So that will be 2 times 2, which is 4, plus 1 times 1, and that gives us 5. We have it right there. And next would be 2 times 1, which is 2, plus 1 times 1, which is 3. And then BA. Let's do that again. B, that's a B, 2, 1, 1. Our A is 1, 1, 2, 1. So 2 times 1 plus 1 times 2, that's a 4. And again, we continue with our first row. So first row, second column. 2 times 1, that is a 2, plus 1 times 1, that's a 3. 1 times 1 is a 1, plus 1 times 2, that's a 3. 1 times 1 is a 1, plus 1 times 1, that's a 2. And you see that AB is very different from BA. So matrix multiplication is not commutative. So if I ask you to prove or disprove the set of matrices is commutative with respect to multiplication, to the operation multiplication, that will be false. But with respect to the operation addition, commutativity holds. So matrix multiplication is not commutative, but matrix addition is commutative. Okay, let's proceed. Identity metrics and powers of matrices. Definition. The identity matrix of order n is the n by n matrix. Sorry, again, a little error by the textbook. It shouldn't be m by n, is n by n, and that is why we call it of order n. The identity matrix is a square matrix, so we represent it by in. We don't say in by m because it's always n by n, so we just say in. So it's defined as that equals the chronicle delta ij. That is delta ij, also known as the chronicle delta, and it is special in that delta ij equals 1 if I equals j and 0 otherwise. In other words, the only positions that have non-zero entries would be the positions 1, 1, 2, 2, 3, 3, 4, 4, and n. And all other positions would have entries 0. So the nth order identity matrix would be of the form 1, 0, 0, 0, 0, 1, 0, 0, 0, right up to 0, 0, 0, 1. Also note that if A is an m by n matrix, that means it has m rows and n columns, then A times the identity matrix In is going to give us A, and Im times the identity matrix A would give us A. The reason why we are multiplying from the right with In and from the left with Im is so that multiplication can be feasible. But I is always a square matrix. Now that we have that defined, we can talk about powers of square matrices. If A is an n by n matrix, that's a square matrix of dimension n, then A raised to the power 0 is just In. So that is almost exactly the same as when dealing with real numbers. 5 raised to the power 0 equals the identity, the multiplicative identity in the set of real numbers, which is 1. In this case, if A is an n by n matrix, A raised to the power 0 equals the identity in the set of matrices, which is In. Also, A raised to the power r is A times A times A times A r times, just like in the set of real numbers. 5 raised to the power 4 would be 5 times 5 times 5 times 5 4 times. Okay? As an example, I3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, by the definition of the chronicle delta, the only entries that are non-zero are the positions 1, 1, 2, 2, 3, 3. Everything else is 0. Transposes of matrices. Let A equals Aij be an m by n matrix, that is m rows and n columns. Then its transpose denoted by AT is an n by m matrix. In other words, if A is Aij, then A transpose is Aji. All the rows become columns and all the columns become rows. And you can also see that the first column has become the first row, the second column has become the second row, and the third column has become the third row. So that is transpose. What do we use this for? Well, if we are going to define what it means for a matrix to be symmetric and skew symmetric, we would have to know something about the transpose of a matrix. So let's go ahead and define what it means for a matrix to be symmetric and to be skew symmetric. We are only going to go so far in this class. This is discrete mathematics. When we come to linear algebra, we will talk some more about the transpose of matrices and then actually do some more fun things with those transposes. So let's move on to this definition. A square matrix A is said to be symmetric if A equals A transpose. As a matter of fact, let me give you all 4 for now, which I think it's good for you to know. Number 1, if A is a square matrix, then we say that A is symmetric if A equals A transpose. Number 2, A is said to be skew symmetric if A equals negative A transpose. Number 3, A is said to be idempotent if A squared equals A. And number 4, A is said to be nilpotent if I can find a positive integer such that A to the n equals 0. And it may not be possible, but I wanted to add 2 definitions in your toolboxes. And the first was what it means for an element of a set to be idempotent and what it means for an element of a set to be nilpotent. But for now, we are mostly interested with symmetric and skew-symmetric matrices. That said, let's move on to 0, 1 matrices. Again, we are simply giving you basic arithmetic of matrices in this section. If we have time in this class, we'll come back to matrices and see how we can use them in graph theory. But it's possible that we will not have time to do that, given that this class has a lot to do with introduction of proofs. So we would most likely see matrices again in linear algebra and probably some more in abstract algebra 1. Let's talk about 0, 1 matrices. Definition. A matrix, all of whose entries are either 0 or 1, is called a 0, 1 matrix, and we use those in chapters 9 and 10. 1, for example, if we were dealing with linear algebra, would mean that those 2 vertices are connected by an edge, and 0 would mean that those 2 matrices are not connected by an edge, and so on and so forth. Algorithms operating on discrete structures represented by 0, 1 matrices are based on what is known as Boolean arithmetic, defined by the following Boolean operations. So we are defining some Boolean operations, and I don't want you to get scared because of the operations, because we have actually seen something very close to this in chapter 1. B1, B2, and this operation, for now, I'll prefer you just to use the word AND. So this will be B1 and B2, and this will be B1 or B2. So what happens if B1 equals B2 equals 1? Well, B1 and B2 would just be 1. Recall back in chapter 1 when we dealt with logic. True and true was true. True and false was false. The only time that AND is true is when both P and Q are true. Otherwise, it's going to be false. So picture that in the same light where 1 would be true and 0 would be false. Okay? So true and true is going to be true. So 1 and 1 is 1 and anything else is going to be 0. Now, do the same with OR. If 1 is true and 0 is false, then it's always going to be true, except we have a situation where both B1 and B2 are false. So 1 or 0 is 1, 0 or 1 is 1, 1 or 1 is 1, and the only time that it is 0 or false would be when both B1 and B2 are 0. So if you can just go back and picture the very first class we had when we introduced the concept of logic, you should be good. Now, we know AND and we know OR. Let's progress in our study of Boolean arithmetic. Let A be the matrix Aij and B the matrix Bij and of dimension m by n. So both matrices have the same dimension. Then we can define the join of A and B, and we can also define the meet of A and B. Simply put, the join of A and B is simply A or B. And if you look at OR as addition and look at AND as multiplication, well, loosely put, A or B or A join B would simply be Aij or Aij, and that simply means I go into the matrices and I join corresponding entries. That would just be Aij or Bij. So that's the join. And for AND, I'll do the exact same thing. I go in and I do AND on Aij and Bij corresponding entries. I call this the join of A and B, and we call this the meet of A and B. So, recall we have defined what AND is between two entries, what OR is between two entries. Now we have defined what OR is between two matrices and what AND means between two matrices. That's the join and the meet. Now we're going to put all of that together and define what is known as a Boolean product. So far we have seen how to execute multiplication of two matrices. Is it the same? How do we deal with a Boolean product? What is it anyway? Let's look at it. Before we hit hard on the Boolean product, let's take an example. So that's the matrix A, that's the matrix B. The dimension here, 1, 2, 3, 1, 2, 3. So same dimensions, so we're good to go. So A or B would simply be, I go into A and into B and I take the OR of corresponding entries. So that is the join. So that would be 1 or 0, which is a 1, 0 or 1, which is a 1, 1 or 0, which is a 1, 0 or 1, which is a 1, 1 or 1, which is a 1, 0 or 0, which is a 0. Remember, OR is 0 if and only if both A and B are 0, otherwise it's a 1. What about the meet? Meet is a 1 if and only if both are 1, otherwise 0. So 1 and 0, that would be a 0, 0 and 1, that's a 0, 1 and 0, that's a 0, 0 and 1, that's a 0, 1 and 1, that's a 1, 0 and 0, that's a 0. So that will be the join of A and B, and this will be the meet of A and B. So how do we put our join and meet together to get the Boolean product of 0, 1 matrices? Now, I do not want you to get confused at all. You perform the operation exactly the same as you perform matrix multiplication. It's just that this time around, instead of times, you'll be using and instead of plus, you'll be using or. That's all. Instead of multiplication, you would use and. Instead of addition, you would use or. So, if A is a matrix Aij and B is a matrix Bij with dimensions that permit feasibility of multiplication, then the Boolean product of A and B is denoted by A dot circle B. So not just A dot B. A dot B would be matrix multiplication, but Boolean product would be A dot circle B, or you can say A circle dot B, whatever we want to call it. And in that case, our entry is going to be almost the same as we did before. Remember, before it was AI1 times Bij plus times, and we should do that using an example. Let A be the matrix defined as follows and B the matrix defined as follows. Let's check the dimension again. 1, 2, 3. So 3 rows, 2 columns. So that is 3 by 2 and this is 2 by 3. So multiplication is feasible. So how do I get the Boolean product of A and B? Let's just pause first and behave as if we were going to do matrix multiplication. If we were going to do matrix multiplication, that would have been 1 times 1 plus 0 times 0 and put the answer in the first position A11, or you can call it C11. But this time around, what are we going to do? Multiplication becomes and, addition becomes or. So that's going to be 1 and 1 or 0 and 0. See that? So the Boolean product of A and B, which is A circle dot B, would be 1 and 1 or 0 and 0, and the next would be 1 and 1 or 0 and 1. The next would be 1 and 0 or 0 and 1. The next would be 0 and 1 or 1 and 0, 0 and 1 or 1 and 1, 0 and 0 or 1 and 1, and so on and so forth. It's a beautiful music. So putting all of that together, the next step would be I evaluate the and And then I evaluate the OR as my last. So that's the first step. The next step, 1 and 1 is 1, of course. 0 and 0, that is 0. And my next step would be I evaluate 1 or 0, which is a 1. And let me just pick this at random right here. 1 and 1 is a 1. Remember, and is 1 if and only if both are 1. Otherwise, is 0. So that's going to be 1. And right there. Or 0 and 1, that's going to be 0 because it's only 1 if and only if both are 1. And or is always 1 except both are 0, so that should give you a 1. And that gives us the Boolean product of A and B, known as A circle dot B. Just as we introduce the powers of matrices, we can also introduce Boolean powers of 0, 1 matrices. And actually, this is probably cooler because we would discover something as we go through this. In regular matrix multiplication, we use the notation A to the R, which was A times A times A times A R times. For Boolean powers, we would use A raised to the power R, but our R is going to be in square brackets. That's the rth Boolean power of the matrix A. And that will be A Boolean product A, Boolean product A, dot, 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 Boolean product A, R times. Wow, that sounds like a lot of multiplications. Actually, it's not. It's beautiful. Okay, let's take an example. Boolean powers of 0, 1 matrices. Let A be the matrix 0, 0, 1, 1, 0, 0, 1, 1, 0. Find A to the n for all positive integers n. Whoa, is that possible? Yes, we can actually find what A to the n would be for every positive integer n. So we start off, first of all, by A raised to the power 2, square brackets. That will be A Boolean product A, and that gives us this. And A raised to the power 3, again, that will be A squared Boolean product A. So that will give us this. We keep going. We go to the power 4 and we have this, and then we go to the power 5 and we end up with 1, 1, 1, 1, 1, 1. Guess what? A to the power 6 is going to be 1, 1, 1, 1, 1, 1. You can try that. A to the power 7, A to the power 8, A to the power 9, and so on and so forth. In other words, for every positive integer n greater than or equal to 5, A raised to the power n square brackets, never forget the square brackets, it should have actually been here also, would just be 1, 1, 1, 1, 1, 1, 1, 1, 1, and then A squared is this, A cubed is that, A to the 4 is that, and A is right here. So that will be an for all positive integers n. And most often you would arrive at this situation where you have 1, 1, 1, 1, 1, 1, 1, 1, 1, except that you end up with nilpotency, where there is an n such that A raised to the power n equals 0, 0, 0, 0, 0, 0, 0, 0, 0, which I think is also possible. And in that case, we simply say for all positive integers n greater than or equal to whatever that number is, an is just going to be 0, 0, 0, 0, 0, 0, 0, 0, 0. And this brings us to the end of our lecture on section 2.6, matrices, again from the text, Discrete Mathematics and Its Applications by Kenneth H. Rosen. This is Dr. Gilbert Eyabi, and I will see you in chapter 3. Thank you and God bless you.